Assalamu alaikum wa rahmatullahi wa barakatuh. We gathered here today to listen to a wonderful presentation by Professor Bimberg, Quantum Dot-Based Flash Memories, the Holy Grail at Sunrise. Actually, Professor Bimberg been with us for the last 6.5 years. We are honored and privileged to have him. Dr. Bimberg actually is adjunct professor at King Abdulaziz University. He is a professor at the Technical University of Berlin. Let me read his bio for you. Dr. Bimberg received his diploma in physics and the PhD degree from Goethe University, Frankfurt in 1968. That's before I was born. And in 1971, respectively. From 72 to 79, he held the principal scientist position at Max Planck Institute for Solid State Research in Grenoble, France, and Stuttgart. In 1979, he was appointed as a professor of electrical engineering, Technical University of Aachen. Since 81, he held the chair of applied solid state physics at the Technical University of Berlin. He was elected in 1990 as executive director of the Solid State Physics Institute at the Technical University of Berlin, a position he held until 2011. In 2004, he founded the Center of Nanophotonics at the Technical University of Berlin, which he directed until 2015. From 2006 to 2011, he was the chairman of the board of the German Federal Government Center of Excellence in Nanotechnology. His honors include the Russian State Prize in Science and Technology in 2001, his election to the German Academy of Science in 2004, to the Russian Academy of Science in 2011, to the American Academy of Engineering in 2014, to the American Academy of Inventors in 2016, as a fellow of the American Physical Society and the IEEE 2004-2010 respectively, the Max Born Award on the, and Medal 2006, awarded jointly, okay, blah blah blah, awarded so many awards, okay, the UNESCO Nanoscience Award and medals in 2011,
don't want to have it.
the Heron Walker Award 2015, and the Nick Holken Award in 2018. In 2015, he was bestowed the DSCHC of the University of Lancaster, UK. Since 2017, he is Einstein Fellow at CIOMP of Chinese Academy of Science. He has authored more than 1,500 papers, 36 patents, and 7 books, resulting in more than 55,000 citations worldwide. Okay, please welcome Dr. Bimberg. Thank you very much.
Well, thank you very much for this wonderful introduction. I'm afraid I have to cut down the time of my presentation by 10 minutes because it took about 10 minutes to read my CV. And I have chosen as co-authors today some most important members. He was talking about himself, of course, yeah, about his contributions to this field. And you see 4 people, I mentioned here 4 people. 2 of them are Islam, 2 of them are Christian, 1 Catholic, a lady, and so we have ladies and gentlemen joined on this piece of work. Multicultural, multi-religious, and 2 genders. Yeah, she's actually a real beauty, Elisa Sala. She does MOCVD, the epitaxial work, which we need for this. And Firat is from Turkey, from Istanbul. He graduated in Istanbul. and was sent by the Dean of Science, also a lady, to my place, and he has to submit his thesis latest tomorrow. Yeah.
Tomorrow?
Yeah, not joking. And actually, a few things I cannot present you. I show you one or two slides from his thesis actually already, although, yeah, I should have waited. But I told him to submit last week, but he didn't manage. So it's this week, okay? And Lisa will submit next month. Yeah? Okay. The Holy Grail, not my invention. It is an invention of a journalist from the New Scientist who reported exactly 10 years ago, when we published the concept of a novel type of flash memory, which is based on quantum dots. And then he wrote this article, which may be Holy Grail of computing. And actually, I put here a question mark. I could actually remove the question mark now. Our latest results, which are also inside these two theses of Firat and of Elisa, show that sun is rising. Yeah. I show you here two pictures. One original picture by Mr. Moore from Intel, the founder of Intel. An old picture, a picture he made in 1965. So, how many years ago? 53 years ago. This is a historical picture in semiconductor technology. And he plotted here on the vertical axis the logarithm of the number of components per integrated circuit, per integrated function. Yeah. And that was already here in 1965. Yeah, the logarithm was already 6. Now you do it a little differently nowadays. You plot the clock speed, and that is a plot of the clock speed. Again, the picture is from Intel actually. Yeah, both are from Intel. You find them in the internet if you search. Between 1960, that's where it started. Actually, 59 it started. But at that time, the clock speeds are very low. That is in megahertz. And the clock speed was below 10 to the minus 2 megahertz, below 10 kilohertz. Yeah, up to 2016. And what you realize is here, despite the fact that you see this logarithmic increase, this exponential increase of the number of components and the logarithmic increase of the number of transistors per integrated circuit, the clock speed has saturated. It's not increasing anymore and since quite some time. Yeah. Point 1. Next, I show you a picture I have shown yesterday already, but today I show it with a different comment. Yeah. Here is the traffic growth enabled by electronic compute storage and access technologies, and this picture is from Nokia Bell Labs in Holmdel, from Peter Windsor. I received it 2 weeks ago from him. He is the head of information technology. Now, he says the following: between 1995 and 2007, the supercomputer performance increased. CAGR means accumulated annual growth rate. So per year it increased by 90%. Microprocessor 40 to 70, and so in storage capacity, yeah. We're going to talk about storage, you say 60. Core router capacity, wireless interfaces, fixed access interfaces, all details which a computer scientist needs to know, and also a person working on information technology. And he plotted on the left-hand side the wireless bit rate, which is going into the computers. Cellular, 60%. And then he plotted on the right-hand side, and that's very interesting now, random access memory and solid-state devices, solid-state memories. And you see that, again, the same sort of leveling out. If you look at in detail at it, it's leveling out. Yeah? It's leveling out. Also HDD, the growth rate is not 60% as he claims here, Peter Windsor, but here it's actually last 8 years or more, 10 years, it is 13%, and here it's flat. Yeah? At the same time, the design cost as circuitry has gotten smaller, the average cost of designing a chip has increased. Right now we are down, since 2014, the first designs at IBM, for example, of 40 nanometer circuits appeared, and the design cost itself, design, yeah, was as published by IBM here, and I found this graphics in Wall Street Journal. Yeah, when I fly a plane, I'm reading Wall Street Journal. It's very helpful. Yeah, 131.6 million US dollars. Yeah, so you have also studies leveling out, as you can see. Yeah, there's not much to do anymore in this direction. Yeah, you can go down to 10 and then end of the story, because then you're going to have tunneling breakdown. Yeah. If you don't know what tunneling is, you go to Wikipedia and read in Wikipedia tunnel effect. Okay? Yeah, it's 80 years old. Yeah? So the average cost of designing a chip has increased. The progress is little. We have to do something else. The present progress is based on Moore's law and actually only on lithography. Immersion lithography, high K dielectrics, extended UV lithography. A lithography machine costs now $40 to $50 million. Yeah, not affordable for a university anymore. Neither for Abdulaziz nor for Berlin. Can't do it. Yeah. So downscaling will be completed, completely exploited, I guess, in 2-3 years' time. End of the story, because tunneling is something fundamental. It's like Newton's law.
Yes.
Yeah, nothing we can really do. What you have to do is you have to go do something else. Otherwise, interface roughness will hit you. What you need to do is you have to introduce new functionalities. If you don't do anything, China will take over, because production cost in China is so low, and IBM will be bankrupt. Yeah, you have to do something else. That's what you're going to do. You see already nowadays, the world's, I have to insert the word second. Until a few weeks ago, I was writing here the world's fastest. Now it's the second fastest. Another came out, which is also in China. Yeah, we have some of the biggest supercomputers of the world are in China. 162 cabinets, 4 frames per cabinet, 16 blades per frame, 2 nodes per blade. So 3 million cores. 30 petaflop, size 720 square meter, 17.8 megawatt. Now number one is now 100 petaflop, a factor of 3 more, which was installed end of last year. Yeah. You see optical links connecting the nodes, and you have, as I say, 3 million cores. Yeah.
The other one is only, how many cores there?
3 million.
Sorry?
3. And the next one has 10.
No,
So
no, I mean the fastest one.
What, 10? 10 million.
10 million.
Yeah. 10. Now, competing with everybody talks about supercomputers. Much more important than supercomputers get always the fame. But what is much more important is data centers. Yeah? And you see here a word, what does it say? Who can read it? Sun. It's one example, one of many. Microsoft Chicago data center, 24,000 square meters. Here we had only 720, 24,000 square meter. Each container contains 2,500 servers. So if you like 25, 255 times 4, yeah, 1 million servers. 1 million servers. Yeah? A server could be the size of this laptop. Yeah? So we have integrated, important is 300 megawatts supplied from 2 power substations situated on opposite side of the data center. And the heat is enough for heating 100,000 people homes in Chicago. So how can that go on? Yeah, not so easily. Now, what are the trends? That is, again, from a paper from IBM. IBM, yeah? I'm reporting. Exaflop, which is going to be the next, yeah? Here is still in the petaflop range. Exaflop mainframe computer demands 3 orders of performance increase as compared to today and demands new technologies. Yeah? Using present technologies for exaflop computers, we would end up at 1.2 gigawatt power consumption. Yeah? Here we have already 300 megawatt, 800 megawatt cooling power. 800 megawatt cooling power. Where would you get this water from in Jeddah? Nowhere. Yeah. Now, usually people talk about 2 things about CPUs and central processor units. They get the glory and are interesting, of course, business-wise. But from a technical point of view, floating point operations is easy. CPUs based on floating point operations. Storage capacity is harder, and as you know, we have many acronyms: SRAM, DRAM, flash, etc., etc., etc. Technically, it requires breakthroughs, and I say after this year. Probably after 2020, but I don't give it more than 2 years. It will not continue below the 10 nanometer limit I mentioned before. Now already interconnects presents the main technical problem, and I talked about that yesterday, yeah? That we do have many problems to solve in the future. One is in optics and one is in electronics. So already in 2009, we have a so-called International Technology Roadmap, which is rewritten every second year. So last time 2017, and today 2009 for the first time, it appeared that the development of an electrically accessible non-volatile memory with high speed and high density would initiate a revolution in computer architecture. And that is the Holy Grail. That is the Holy Grail. Because this sentence means that you have to marry DRAM with flash. Because these are opposing non-volatility and high speed. Yeah? Either or. Because a DRAM is fast. Fast access time, good endurance, but volatile. The information stored in a dynamic, that's why it's called dynamic, in a dynamic RAM, is stored there only a few milliseconds. Yeah? Less than a blink of your eye. And it's energy expensive because you have to refresh the information every millisecond. And that costs enormous amounts of energy. Yeah? That is one of the main sources of spending energy.
Excuse me, in the roadmap, there is no mention of power consumption.
Where?
Sorry, in the roadmap, it is only the non-volatile.
No, it's also a mention of power
be.
consumption, many more details. The roadmap, the book has 1,000 pages.
I see.
It mentions yeah, I mean, you could teach probably two semesters about just about the roadmap and about materials, many different materials. Say,
The power is there as one
of course,
main factor.
of course.
Of course it is.
There is actually a section on quantum dots also. I don't show. Yeah? Because I'm the section on quantum dots. A flash is non-volatile, which means the storage time is 10 years or more. More. Yeah? Because in my mobile phone, this is already the third or fourth generation of mobile phone. And you have, of course, your telephone book on the chip, on the flash. Yeah? So what happens if suddenly the telephone book mixes up the various telephone numbers of your girlfriends? A catastrophe is going to happen. One person smiles. Yeah? I know you shouldn't talk about girlfriends here. You should talk about, I don't know, boyfriends or whatever, or family? Okay. Family, sisters and brothers.
Certainly not boyfriends.
Yeah. Okay, 10 years storage time. Very energy efficient. No refreshes needed. Yeah, actually not possible. Refreshing is not built in that. But bad endurance. Yeah, if you call the same number more than 1 million times, smile please. More than 1 million times, after 1 million times or so, you will have an error and one digit is going to change. I can explain you. And it's slow. Yeah? The access is slow. Yeah, now a microsecond is okay for dialing a phone number, right? Or writing a small message. Now a quantum dot based flash, a flash is based on a quantum dot, enables now the new functionalities. The DRAM and flash converge and leads to an energy saving. That is your question, computer architecture. The point is also, when you design a computer, yeah, you use architectures and you have both types of memories inside. Yeah? That means that you have a very complex architecture, and the architecture itself, having both types of memories, is of course costs money, yeah, and costs energy, because you are sending across all the time information from a solid state memory, for example, to a dynamic memory. It's always information sent around. Yeah? And in the moment you would have one type of memory only, a computer would simplify enormously. Enormously. That would be a big advantage. The data transfer from SRAM or flash to DRAM can be eliminated. And there are, of course, competitors. We have an advisor in my project. We have a very big project from the government where I get close to 2 million euro from making such memories. But there is the head of development from Infineon is our advisor. And he tells us, there is a competitor phase change memory, but you're better. So quantum dot itself might reduce memory energy consumption by 3 orders of magnitude. Sure. Yeah.
By the way, what is
So it's the
phase change memory? Is the spin of the... Can you say a little bit about what is the phase change memory?
At the end of my talk, if you still have the power, asking question, because it's a completely different subject. Phase change means change amorphous to crystalline. Yeah? And that has different reflection coefficient, etc., etc., etc. Yeah? So the ultimate memory, these are the demands. The ultimate memory has a fast access time, 10 nanoseconds or below, is non-volatile, more than 10 years of storage time, and allows more than 10 to the 15 write cycles. Not 10 to the 10, but 10 to the 15. Yeah? And you need that because you're writing every millisecond. Now, we're holding patents. Actually, the patents were submitted a few years ago, and we just got them in the last few months. It takes always a number of years, and we submitted several patents, and it's quite interesting. We got all at the same time, within 2 months. But we had to kind of exchange of arguments for quite some time with the US Patent Office, and also EP means European Patent Office. Yeah. Now, 20 more minutes, sir?
Yeah, fine.
20 more minutes, is that okay?
Yes.
Also? Yeah, 20 more minutes. So I will give you some details about the concept, and then the rest I'll run through a little. The basic idea is don't use the silicon dioxide system anymore, but use 3,5 compounds. And people might argue, why 3,5 compounds? We're living in a silicon world. No. We had already in the 90s, which is 20 years ago, supercomputers based on gallium arsenide, gray, convex, but they were too expensive because they had to be cooled with liquid nitrogen, yeah, and so they were not competitive. We have a wide variety of 3,5 compound materials, you see here, which you can combine all and plus doping. So you can use controlled band structure engineering, tunable barrier widths and heights, and handling the trade-off between the write speed and storage time. So what we essentially use is a heterostructure. That is a heterostructure here as a memory unit. Very similar to a laser, actually. Yeah? Except that in a laser, you have an electron, you have a hole, they recombine, and a photon is emitted. Now, do you need both for a memory, electrons and holes? No. Not at all. No. Actually, it would be very bad, because then they would recombine. And what you do want is not recombining, but keeping them. Yeah? So we can combine and create very deep potential wells, depending on which material we are combining with. Let's say combining indium antimonide with aluminum phosphide. Yeah? But then we have the problem, we don't have the same lattice constant, and we cannot make, let's say, quantum wells because of strain. Yeah? And we're going to get dislocations, defects. Larger band offsets, that is a band offset. Yeah? Band gap difference, large band gap difference, large lattice mismatch, but high strain in the heterostructure dislocations. Now, what I introduced for the first time is don't use these types where you have, when you inject carriers, you can keep electrons and holes. Do something different. You have so-called type 2 band structures in semiconductor physics, in semiconductor technology. Yeah? Technology means you make it, physics means you design it, you have an idea. Okay? That was type 1. But for the same band gap difference, yeah, the band gap difference is the difference between this band gap with that band gap. Yeah? You have here small localization energy for holes, and you have electron localization, so you can have recombination you don't want. Type 2 is that. The band gap shift, it goes in the same direction. Yeah? You have a larger localization energy for holes, and you don't have any electron localization. Which means also much smaller tunneling probability, and that enables multi-level functions. Yeah? This is a different subject. Don't ask me for that. Multi-level operation, multi-logic operation. Yeah, enables type 2. So, quantum dot concept is the following: you deposit one type of material which has a different lattice constant, like indium arsenide. Yeah, you see here, close to 6.1 on gallium arsenide, 5.7. You deposit it, and then after one monolayers or two monolayers, you get strain relaxation. That means you get a decomposition of the deposited layer, and you get self-ordered three-dimensional quantum dot growth. And behind that is a first-order phase transition. No physicists around, so no question about this subject. First-order phase transition, that means just you release energy. By forming here pyramids, you release energy.
Minimum energy.
Less strain, higher localization energy in quantum dots, and here you see a picture, a three-dimensional picture. Yeah, this picture was made with scanning tunneling microscopy in an MBE machine. And for forming such quantum dots, you don't need lithography, yeah, but it's self-organization. And you can create a very high density of such dots, terabit. That means a memory can have a terabit per square inch, which is record, yeah, if you would fully exploit it. And finally, what we have developed is precise localization of single dots using stressors. So you can precisely localize it, yeah. Again, a material science subject, not something where you would be really interested in, but probably the Nanotechnology Center, which we visited an hour ago, how to localize such quantum dots. So what we're going to use is now, we use the self-organized quantum dots as memory units. We are going to use holes, not electrons. Yeah, always keep in mind, as an electrical engineers are used to thinking about copper leads and there are electrons and so on. No, stupid. You have electrons and holes. Of course, in copper leads you don't have holes. In actual fact, if you think about it, you have holes, but
absence of electron. An absence of electron is a hole.
Absence of electron, yeah. In a tetrahedrally bonded semiconductor, yeah, and then that is a logical This is a logical zero, having a binding potential, but not filled, and here a logical 1, yeah. Now you embed them. Now it starts to become complex. We go now a little deeper into electrical engineering. Device physics is electrical engineering. Yeah, what is MOSFET? Modulation doped field effect transistor. You take a field effect transistor structure. We know about that. We have a quantum dot layer. We have a two-dimensional hole gas, p-type doping, and that is a band structure. Now, band structure is something actually. My first position, which was mentioned by Dr. Ashur, was at the Technical University in Aachen, where I got a faculty position as a physicist, which sounds a little strange, but the faculty decided that the students in electrical engineering should be taught about band structure, and I was a band structure specialist. And actually I did the same as the Nobel laureate Herbert Krömer, who is in Santa Barbara in electrical engineering department. Herbert Krömer got a Nobel Prize in the year 2000. Not such a long time ago, for you a long time ago, for me not, and for working on band structure, designing double heterostructures. So that is a band structure here. You have here now a hole Yeah, it's filled and the band structure looks a little complex, and here you have p-type doping. That is schematically the valence band diagram. Now a little more in detail. Which operations we need? Yeah, what are the conditions which such a structure has to fulfill? Storage of logic 1. That is storage of logic 1. We decided having a hole inside is logic 1. Okay? Emission barrier prevents holes from escaping. That is the emission barrier here. Yeah? And the emission barrier must be high. Yeah? That is not escaping. And that is given by the localization energy of the conductor. That means the difference between this point here and this corner here. And if they can escape, they would go here. But they should not. Emission processes in quantum dot in general. One is thermal excitation. Another one is tunneling. Now thermal excitation is not happening if the barrier is high enough. Tunneling is not happening if the barrier is large enough. And finally, unfortunately, you can combine both, which is bad, which is a pity. We have thermally assisted tunnel emission. And then it goes only to the excited state. The energy difference is much less of holes. And the barrier which is smaller, and then you have thermally assisted tunneling. So what you really have to do when you design, you have to look at that third point, thermally assisted tunneling. You have designed in such a way that also that is not happening. Emission rate is depending on the square of the temperature and the so-called capture cross-section, and exponentially on the localization energy EA. Yeah? Exponentially. So it's a linear dependence here, but an exponential dependence here. And apart from temperature, it's very fortunate you have only two parameters to think about, to modify. Only two. It's comparatively easy. Easier than, for example, cutoff frequency of a laser. So, activation energy and capture cross-section.
What's gamma?
Is a parameter, is a constant.
Only constant.
It's a constant, you can calculate it, etc., etc. Memory operations, now writing. Now you change the bias. Now dashed line is here. Yeah? And you pull the voltage down, you pull it down, yeah? You apply a positive bias here, positive voltage here, you push it down, and then you can capture carriers which are here in this 2D layer. Yeah? Forward bias eliminates the capture barriers and hole get captured in quantum dots. That is extremely fast. I say here it's picosecond, it's actually can be faster than picoseconds, it can be down to 500 femtoseconds. Very, very fast. Yeah? Very fast. So certainly no problem. Erasing. You do exactly what I discussed before. You do the opposite. You pull this energy level of the valence band, instead of up, you pull it down. And then you have a tunnel emission. You have a smaller width of the barrier, yeah, and you get it out. Reverse bias narrows the barrier, you have an enhanced thermally assisted tunnel emission. And the width of the tunneling barrier is, of course, tunable by external voltage. Very straightforward, very simple. Read out, you do some p-type doping. Readout is done via conduction measurement here. Holes in the quantum dot deplete. The two-dimensional hole gas is here, which you generate by p-type doping. Here is a hole gas, and you deplete it by you deplete the whole gas by the quantum dots, by the holes in the quantum dots, and that they lower also the mobility, and then you have remote impurity scattering, and that is the way. That is actually the way to control how much, which of the memory units are populated. So what has been done so far? Storage time, number one. Write times, erase times. And I will focus a little on the storage time, and the rest I will kind of run through. We use a measurement method which is called capacitance spectroscopy. That is an electrical engineering method where you measure the capacitance, C, as a function of voltage. Yeah? And there is a method, variation of that, you do it time resolved, like time resolved luminescence. Yeah? You excite a subject, you look at the decay of light, you can look at the decay of capacitance. Yeah? It's much closer to electrical engineering than luminescence. And at 300 Kelvin, you need a minimum of delta EA of 60 milliwatt. Then, yeah? 2.3 times 26. And finally, if you want to have such a memory where the information is stored for 10 years. 10 years, okay? 10 years, flash. 10 years. You must end up at this line here, I show here, between 1.1 and 1.4 electron volts. Yeah? 1.1 and 1.4 electron volts. Yeah? But we do not know about this number here. Yeah? That's difficult. That's the subject of the thesis of Elisa Sala to find out. Now here I have collected data. We have worked on this subject for quite some time, and we had several generations of PhD students. You see 2007, 2013, 2015. Here Sala appears for the first time. Yeah? And we started with this material system, which was type 1 band structure, and which turned out, after some thinking, it's inappropriate. Yeah? Then we went to type 2 systems, silicon germanium. We would have loved if silicon, get germanium quantum dots in silicon, if that would have worked out. Unfortunately, the binding potential is too little. Then we went to antimonides, and we are still with antimonides. We're working now on antimonides with embedded in antimonide quantum dots, gallium antimonide quantum dots embedded in aluminum gallium arsenide, or indium arsenide embedded in aluminum gallium arsenide. Yeah, with 90%. Yeah, here we finally ended up at 1.6 seconds. And where did we start? Now here at 10 to the a nanosecond. So we managed 9 orders of magnitude improvement. 9 orders of magnitude improvement is not very often that you manage personally such, yeah, something like that. Usually you manage 9%, but not 9 orders of magnitude. Yeah. Right now, we're working on a material system which was never done before. We were the first to make it. We have gallium antimonide quantum dots embedded in gallium phosphide. Yeah? That is here, and we measured also the capture cross-section, which is here at that point. If it would be 10 to the minus 15, we would be at 10 years. Nature told us, the experiment told us, we are just in the middle of these lines here. Yeah, we are at 10 to the minus 12. Yeah. Now, next step. We have increased by now. We are here at 4 days. 4 days. This is the very last achievement. We have increased the storage time by not 10 but 14 orders of magnitude. Yeah? And next step is replacing the gallium phosphide, the gallium atom, by aluminum, using aluminum phosphide. Now, for somebody who is familiar with semiconductor technology, fortunately nobody is here, because he would immediately yell and say it's impossible. It is possible. Everything is possible. You just have to work on it for some time. Yeah? And with aluminum phosphide, and here we're working with a group in France, actually, with aluminum phosphide, we will manage to go up here. And in addition, the work of Sala showed us that we can indeed go across about 6 orders of magnitude of the capture cross-section by changing the size of the quantum dots. Yeah? Because it's very simple. Bigger quantum dots have a larger capture cross-section. Yeah? So what do you want to have? You want to have a smaller or a larger capture cross-section? Look at this figure. Tell me. Which one would you like to have? You were the first one coming in this afternoon. And look at it. Would you like to have 10 to the minus 15 or 10 to the minus 9? No.
Think about it. Look at the storage time.
Which one you want to have?
This one.
Less sigma. He's asking about sigma. And look, sigma to minus 15 goes to the
Yeah? Okay. You want to have small. So I was saying the capture cross-section goes with the size of the quantum dot. You want to have small quantum dots or large ones? Small ones. Now if the quantum dots are smaller, you can have also a higher density. So it's a double whopper. Yeah? It's good. What you have to make small quantum dots, but with a large localization energy, and then you get at the same time a large storage time and a large density. Right? That's what we're going to have. Now,
Sorry, let me ask a question.
Yes, please.
Also, that is multi-level thing you talked about. I mean, when you do this reduction in size, the quantum dots, does it affect also the multi-level behavior that you talked about?
It affects the multi-level behavior. The smaller the quantum dots are, the larger the difference between the energy level is. Yeah. Now holes have very closely spaced energy levels. Yeah. And actually, it is good for multi-level operation if the energy levels are a little more apart from each other. Yeah. That is an advantage. Yeah.
So that will reduce the probability of tunneling also.
Yes. Well, yeah, and I'm not going now to talk about right and D and so on and how, what we...
Maybe I have another question, just quick question.
Yes, please.
Regarding also, I mean, the trick here, or the thing is that it's changing the sort of material that is used to produce the thing. Now, 2 questions. Is there anything else besides this that you can do, beside the material to improve the storage? And then this curve that you've shown, I mean, which is theoretical in a sense. Do you think that there is maybe a saturation at some time?
Point 1, it's always, whenever we have progress in science and technology and engineering, it's material. Let it be high temperature superconductivity, let it semiconductors, let it nitrides. Yeah, yeah. What we're working on in the aluminum nitride, gallium nitride area is UV, generation of UV for water cleaning, yeah, for bacteriological water cleaning. the basis of everything is material science. Yeah, you have a floor which is not concrete because concrete kind of
Material science is.
yeah, material science is fundamental. You cannot escape material science. If you talk about electronic circuits, you have, I mentioned at the beginning, high K, low K dielectrics. It's material science. Point number one in your work is also always mastering material science, but you need a goal. Yeah? And so, okay, that is enough for answering. And now I want to come right to an end and show you a little what the subject of the last student is dealing with the tunneling. Yeah? We have actually prototypes which are working, and I will come to the very end of the presentation, future challenges. Increasing storage time, faster write time, faster erase time. So these are the materials we're working on. These are the materials in blue. Yeah? These are the materials which we have done. 1.4, so we replace a little the gallium by 50% indium. We don't gain so much. Yeah? It's not worth the effort, but that is worth the effort. And indium gallium antimonide. Yeah? So we are ending up here, and that's enough, definitely, whatever the capture cross-section is. So antimony-based materials in combination with P-based matrix are promising. Faster write times, this is easy because this is just a classical electrical engineering subject. You have to work on RC. Yeah? It's just the size of the, we are not using nanolithography. Yeah, we have only micrometer lithography. Now, tunneling is more difficult. And that's the subject of Firat Arikan. Remember, he has to deliver tomorrow latest? Okay, let's see. The problem is the storage time is increased by increasing the localization energy. Longer storage time means longer erase time. Yeah. So how are we dealing with this subject? Now you just need to have a little know-how. It's called transparency engineering. We put in several other structures here, layers here, with superlattices. Yeah? What we want to have in the storage time, very small transparency and no overlap of all these energy level positions with the energy level positions in these quantum wells now. These are quantum wells. Now by changing the bias, you immediately introduce erasing the tunnel through. And tunneling is in nanoseconds or less. So you have in the erase state a very large transparency. That is actually the matter of a pattern, and that's now his calculation. This is very complex now already. You see here many different layers, and doing the calculation is stress, and he did a lot of theoretical work on the computer, yeah. But it works now, and you can see that you can modify the transparency by at least 7 orders of magnitude by changing just by a few tenths of volt. Isn't that fantastic? Yeah, and that is working. Signal resonance for high light holes, 7 orders of magnitude. You have a storage position and you have a erasing position, and here at 0 volt, and actually here you're at 4 volt, which is very easy. Yeah, and you can get actually more. You have also a resonance for heavy holes, 8 orders of magnitude difference. You have different erase positions. So storage erase ratio is between 17 and 21 orders of magnitude. Okay? Yeah? Conclusion. We're at the end. The concept, a quantum dot is a storage unit embedded in a MOSFET structure. It works. It has the advantage of material voltage tunable barriers. We have fast write times. Presently we have 4 days. I expect that we're going to have within a year or so, more than a year at least. Increased as compared to our starting point by 14 orders of magnitude. So I can predict non-volatility, write time demonstrated to 6 nanoseconds. We are solving now the trade-off for the erase time. We have a first demonstrator. We expect with the current materials to work at room temperature, and the roadmap for the next generation is gallium antimonide in aluminum phosphide or gallium phosphide or embedded in aluminum indium phosphide. That is a MBE material system, and that's a MOCVD material system. We don't care as long as it's going to work. Thank you very much for your attention.
Thank you very much indeed, Professor Bimberg, for this insightful presentation. We have thoroughly enjoyed the presentation, and we have learned a lot from the presentation. If anybody interested to ask any questions, please do. The floor is open for 2 or 3 questions. Please take this, because we're recording everything. To ask a question, please speak to this.
What is the difference between Q-dot technology and quantum machine technology?
Between what?
Quantum machine technology and quantum dot.
What is quantum machine technology?
Quantum computing.
It means quantum computing.
Quantum computing. In quantum computing, you use so-called qubits, quantum bits, which are polarized photons, for example. And here we're working not with photons, but with electric charges. Okay? Next question. Yes?
Anybody has any question?
Faculty is also allowed now.
Faculty allowed? Any student? Student first. No students? Okay, Dr. Abid, please.
So the last important.
No, not really. But the nice thing is that you already know what sort of future material you will use for the next and the third. And the question is that how this is already planned? Is it simulation? Is it...
Yeah, it's a simulation. It's band structure simulation. We calculate. We have developed quite some time ago already a program which can be now downloaded from the internet also. Some competing group with us has put the program in the internet, so-called 8-band K.P calculation of quantum dot energy structure. And based on that, we can make predictions, and the predictions numerically hold. Because this is 10 years of development of the software. 10 years. Three generations of students. Yeah?
So basically, okay.
And that works.
Yeah.
Fortunately.
Yeah,
The challenge is not so much the calculations. The challenge is really making the materials. Yeah? Because a combination of aluminum and phosphorus is the worst case situation you can imagine.
But does this mean that if you want to have the conditions of fast arrays and long storage time, you are at a position from calculation point of view, you know what sort of material, but maybe it is very, very tough or close to impossible now to realize this. Am I right in saying so?
Say it again?
What I'm saying is that, okay, you put here actually 2 or 3 types of things that you want to try. Okay, and these, due to calculations, you know what are the properties of these? In terms of
Well, you know some of the properties, but you do not know the material. You know the band structure of these materials, but you do not know how to grow them.
yeah, okay. Yeah.
That is something you cannot calculate. That is something you have to try out. That is the experimentalist has to do.
What I meant is that it is from calculation you could know the results, but how to reach that, this is the problem.
Yeah,
And that's why you have to go through
Correct.
intermediate steps.
yes,
to-
correct.
To have this knowledge in during the process.
Well, first of all for getting the money, for example, very simple, getting money from the government, and we got a huge amount of money, and from National Science Foundation altogether, I think 2.5 million euro. So how many real is this times 4 or 12 to 11, 12 million real? That is something we have to get first, and you're not getting so easily. First, you have to give a proof of principle. And we managed to have the proof of principle with the material system which we mastered. Then we started with the material system which we did not master, and I gave, for example, some money away to some other group in Germany, and they failed completely. Yeah, they completely failed. They were not good. Material science is only for good scientists, not for bad scientists. Yeah. Then I had still somebody left. I gave it to a group in France, because in Germany we are in European Union. I can give national money, like Saudi Arabia would give money to the Emirates, or other way around, or to Kuwait, yeah, or to Oman, yeah. So I gave money to a very, very good group I knew about at the University of Lille in northern France. They managed, yeah. And then a little later, my own people were catching up, but we have a different system. One is ultra-high vacuum system, molecular beam, epitaxis. The other one is MOCVD. MOCVD is what we have. And we are catching up now with the work of Mrs. Salah. Yeah. So a few things you can calculate, but at the end is still some work left for you. Yeah. Yeah.
You have a question? You have a question?
Yes. What did you call it, Holy Grail? What did you call it, Holy Grail?
What is your?
Holy Grail. What do you mean by Holy Grail?
Oh, yes, the Holy Grail is the flash which is as fast as DRAM, a nanosecond fast, and keeping the information for 10 years.
Okay.
Thank you very much, gentlemen,
we
for
have
your
to-
attention.
Yes, we have to conclude now. Thank you very much indeed.